Derivatives of trigonometric functions. In this lesson, we will concentrate heavily on trig functions, which means we will be using all of the rules that we've learned previously and now throwing in trig functions in every single example. So you can see here that the derivatives of the trig functions are as follows. Here's an entire list of them. We have the derivative of sine of x equals cosine of x. The derivative of cosine of x equals negative sine of x. The derivative of tangent of x equals secant squared of x. And we have three more down here that you can see for yourself. You have seen all of these before, but we will start concentrating on these derivatives in this particular video. So one thing I've mentioned already is that you will use the rules you already know, such as the power, product, and quotient rules, with trig functions in every exercise. You will still be finding the slopes of tangent lines and the equations of tangent lines, and there is still going to be this idea of rewriting, and that is just more so than, say, rewriting a square root as x to the 1/2 power. So on this slide, I review with you some trig identities up here just to make sure you understand how to rewrite some given trig functions in terms of other trig functions. So you can see here are the reciprocal properties. You will need to know these very well. In fact, all of these, the reciprocal, ratio, and Pythagorean identities, all really well so that you are successful with finding the derivatives that involve trig functions. So the reciprocal functions are all here. These are pretty standard. What you should know: sine is 1 over cosecant, cosine is 1 over secant, tangent is 1 over cosine. Cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. These will be necessary for you to know pretty much throughout the rest of calculus. Like all the way, calculus 1, 2, and 3. Then we have these ratio identities, and these are what tangent and cotangent break down into as far as sines and cosines are concerned. So tangent is sine over cosine, cotangent is cosine over sine. And then lastly, everybody's favorite favorite trig identities, the Pythagorean identities, and that is sine squared x plus cosine squared x equals 1. 1 plus cotangent squared x equals cosecant squared x, and the last one, tangent squared x plus 1 equals secant squared x. So knowing all of these trig identities will be very helpful. As far as the half angle and double angle formulas are concerned, they may be helpful for you to know, but generally those only get used very infrequently. And when we start talking about the chain rule in a few lessons, the double and half angle formulas don't necessarily need to be known. And we'll get to that more when we cover the chain rule. Examples. On this slide, you can see that there are two examples, the first of which we will talk about finding dy dx if y equals the square root of x times tangent of x. And so what you will want to do first is rewrite this as x to the 1/2 power times tangent x. And I hope that you notice that there is this multiplication happening here, which means that you will need to use the product rule for this derivative. That being said, we will need to find y prime, or I guess we're finding dy dx here, dy dx will equal the first, which will be x to the 1/2, times the derivative of the second, which is tangent x, plus the second tangent x times the derivative of the first. So the derivative of x to the 1/2 power. So then all we need to do to complete this derivative is to find these little derivatives within here. So that allows us to write x to the 1/2 power times secant squared x plus the tangent of x times, by power rule here, for this term, will give you a 1/2 x to the negative 1/2. And I'm going to go through and actually simplify this one so that you can see what the simplified version looks like. So this is the unsimplified version. This is just a sufficient answer. So I'm going to write unsimplified. Since this x will end up in the denominator, that means we will have a fraction. You can see we will have 2x to the 1/2 power in the denominator over here. So I also want a 2x to the 1/2 power in the denominator over here, so I can make this all one fraction. So what I'm going to do is multiply this term only by x to the 1/2 over x to the 1/2. And when you do that, when you multiply this, the x to the 1/2s come together as a whole x, so this will equal x times secant x squared x. And actually I want to multiply this by 2x to the 1/2 power, so this will be 2x times secant squared x plus tangent x. And what multiplying the top and bottom here by 2x to the 1/2 power does is it gives us a common denominator over here and over here, allowing us to create one fraction for our simplified answer. Now there's nothing that seems to be readily common factored out of these two terms. So that's it. This is the simplified answer. For this next example, you are asked to find d squared p over d theta squared. And in order for this to work over here, I need to have a theta here where secant is, so secant theta. There we go. So the function, you can see now, is p equals -5 secant theta. So we can find the first derivative of this just using the now the knowledge of the derivative of secant, meaning dp d theta is -5 secant theta tangent theta. Then the next thing that we need to do is find the derivative of the derivative. And what we need to recognize here is that there is a product here now. So we can write that the second derivative, I'm going to do this in purpley color, the second derivative equals -5 times the first function, secant theta, times the derivative of the second function, tangent, plus the second function, tangent, times the derivative of the first function, secant theta.
And what we need to do now is very similar to what we did up here. All we have to do is take these little derivatives to get our final answer. And maybe we have to simplify. Let's see what happens here. So this is -5 times secant theta times the derivative of tangent theta, we can see from up here, is secant squared theta, plus tangent theta plus the derivative of secant theta is secant theta tangent theta. So when you multiply all of these things together, you get -5 secant cubed theta plus tangent squared theta secant theta. Right, and that's because over here there are two tangents being multiplied. It's tangent squared, one secant, secant cubed. So that's a derivative, and that is unsimplified, but there's one thing that we can do here, and that is common factor out 1 secant theta from both sides, or from both terms. So our second derivative will end up being -5 secant theta times secant squared theta plus tangent squared theta. And you might think that this can simplify by some sort of Pythagorean identity, and it does not make it any simpler. We can represent it different ways, but it does not make it any simpler. So here is a simplified answer for the second derivative of this function. And let's see, I think this one here or this one here would be considered an unsimplified derivative. Some more examples. Here we have a function q equals 1000 minus a squared cotangent a, and we are asked to find the derivative of q. So the first thing that we're going to do if we want to find the derivative of q, or q prime, is remember that a constant, when you take the derivative of a constant, you get 0. And here still we have a multiplication, so we need to use the product rule here. So it would be 0 minus the first times the derivative of the second. In this case is cotangent a, so I'm going to write d dA cotangent a plus the second times the derivative of the first, a squared. Now you may notice that I put these parentheses around the entire product rule, and that's because the entire product comes after a subtraction. So we need to make sure that that -1 gets distributed to all the terms. All right. So when you take the derivative of all of this, you'll get q prime equals, let's see, the derivative of cotangent is negative cosecant squared. So we'll end up with negative times a negative is positive a squared. This is cosecant squared a plus cotangent a, and the derivative of a squared is 2a. So with some quick rearranging, you can see that there is an a in common in both terms, here and here. So common factor out an a, So this leaves you with a cosecant squared a plus 2 cotangent a. So there is a simplified answer for that one. And in the next example, you can see that we're asked to find yet another derivative. And we have this monstrosity looking thing here. Cotangent of t minus cosecant of t over cotangent of t. And the way to go about finding this derivative is to use the quotient rule. We've got the clear fraction here. So remember, you will always start and end with the denominator. So this will be ds dt equals cotangent t times the derivative of the numerator, which is cotangent t minus cosecant t. Subtract the numerator, cotangent t minus cosecant t, times the derivative of the denominator, so derivative of cotangent t, all over the denominator squared. So cotangent squared t. I have a feeling we're going to be doing a lot of simplifying here. Let's see what happens. We have to find the derivatives of these little pieces now. So the derivative of cotangent t minus cosecant t ends up becoming negative cosecant squared t plus cosecant t cotangent t. And that's because when you take the derivative of a cotangent and the derivative of a cosecant, you'll get a negative answer. So this first term will turn into a negative term, the second term will turn into a positive term. So then the only other derivative we need to figure out is over here. And cotangent t, and you can remember from the example above, cotangent t turns into cosecant squared t. So this is negative cosecant squared t. And everything else follows exactly the same. And remember that there's multiplication happening here, so this is cotangent t times that derivative minus cotangent t minus cosecant t times this cosecant squared t over here. Oops. There we go. And this is all still over cotangent squared t. As for simplifying this, you should notice that in the green text here, you can common factor out a cosecant t. And so what I'm going to do is I'm going to common factor that cosecant t out of there, but also rewrite this with the cotangent first, because you'll see why here in just a second. So when you common factor a cosecant t out of this set of parentheses and rearrange the terms inside this set of parentheses, you'll end up with something that looks like this. So here you can see the cotangent t is still there. The cosecant t that was factored out of this set of parentheses is now in front. And if you take out a cosecant t, you're left with a negative cosecant t inside of the parentheses and a cotangent t inside of the parentheses. So there are those two. And then over here, I just multiplied this negative times this negative to make a positive cosecant squared t times this set of parentheses right there, all over cotangent t. So now you can see that in the numerator, we will be able to common factor out a cosecant t, and we will be able to common factor out a cotangent t minus cosecant t. This problem will continue in the next slide. So here is the information that we had from the previous slide. And I mentioned that we want to common factor out a cosecant t and a cotangent t minus cosecant t from each term in the numerator. So when you do that, the numerator will look like cosecant t times cotangent t minus cosecant t. So if we get rid of these these factors from the first term, you'll end up with cotangent t plus, and if you get rid of one of these here and this factor from the second term, you'll end up with a cosecant t. Oops, square bracket. And this is all still over cotangent squared t. And if you'll bear with me for a few more steps, we are almost done. Here, something funny happens. You notice that we have a difference of squares factored out already. So if we multiply these things together, you end up with cosecant t times cotangent squared t minus cosecant squared t all over cotangent squared t. And if you can recall all the way back from a few slides ago, these two trig functions are in the same Pythagorean identity, and that this whole thing here will simplify to -1. So now we have this this entire term, or this entire factor, being equal to -1. Well, now this gets really simple. This is negative cosecant t over cotangent squared t. And you can manipulate this fraction to include trig functions that are not fractions. So if you can do that, please do that. This ends up becoming negative cosecant t tangent squared t.
And because of the nature of trig functions, this answer and this answer can both be rewritten many, many different ways. For example, you could write that the cosecant is -1 over sine t, and that tangent squared is sine squared t over cosine squared t, leaving you with a cancellation of a sine t. And now you have a sine over cosine squared, which is the same thing as writing negative sine of t times secant squared t. So there are a lot of different ways that you could end up representing this answer here, as this fraction, as this product, as this product. You will just have to be familiar with the trigonometric identities in order to reach a good answer. In this final example here, you can see that you are being asked to find the second derivative if the function is equal to this over here. And this looks scary. This looks like -2 is a constant, and then over here you would want to end up using the product rule. But that is not what you want to do in this case. You could if you wanted to. I won't stop you. It won't be wrong. But in this case, it would be much better if you multiplied these two products together. Or sorry, multiply these two factors together and get that y equals -2 times secant squared x minus tangent squared x. And if you can remember from a few slides ago, the Pythagorean identity that involves secant squared and tangent squared, as tangent squared x plus 1 equals secant squared x, if you subtract tangent squared x from both sides, you can see that secant squared x minus tangent squared x equals 1. So I'm going to make this whole substitution here for 1 times this negative 2. So finally, we just have this y function equaling negative 2. So if you take the derivative of this, dy dx, well, the derivative of a constant is 0. And since 0 is a constant, that tells you if you take the second derivative, d squared y dx squared, that means you also get 0. And if you go through and do the product rule and simplify it down all nice and cleanly, eventually you'll end up with something minus itself, which will give you that 0. So if you want to, you can go through and try doing the product rule to see if you still get 0. But in this case, it is easier. It is good for you to recognize that secant and tangent are in the same Pythagorean identity, and that when you multiply these together, you get some version of the Pythagorean identity, thereby making this derivative much, much easier. All right, hope this helps. Good luck.